Hello everybody, welcome to our first explanatory video about chapter 7 corresponding to the first paragraph. In this chapter we're going to explore the relation between forces, so how hard we push or how hard we pull on something, and the speed that it will get. Now this may seem pretty obvious. We're quite used to the fact that when we push something forward, it will get a speed in forward direction, and we pull something backward, it will get a speed in the backward direction. However, there's more to it than that. Well, I'll show you a simulation to show you what I mean. Okay, so here's a little tug of war. I have a cart here filled with candy, and I can place these guys to the left and right. When I only push this guy here, then this arrow indicates the force that he's exerting on the cart. So if I press go, he starts pulling the cart to the left. When I put an extra guy there, and that guy is also exerting force. Since they're equally strong, the sum of the forces, that means the force to the right and the force to the left together, is 0. So when I press go now, nothing happens. They're both equally strong, so the cart doesn't move. When I add an extra red guy, the force to the right is larger than the one to the left, so there's a sum of the forces, and red team wins. Still, no surprise. So let's start out like this, and if I then pause it, card is moving to the right now, but I've paused the simulation. If I now add another guy to the left, then force to the right and force to the left cancel each other out. The sum of the forces is 0. So if I press go again, you might expect that the cart would stop. Let's do it. The cart doesn't stop. The force on the cart is 0 because the forces cancel each other, but the cart simply keeps moving. The reason for that is the following. Force doesn't directly change speed, but gradually. When there's no force on the cart, the speed of the cart doesn't change. When there is a force on it, then the speed to the right will increase. But when I remove it again, the speed will remain constant to the right. And if I add another guy to the left, let's put 2 because I might be a bit late, then the speed is first reduced and then increased. And when I remove these 2 guys again, the speed remains constant. So, very important conclusion here. A force working on a cart changes its speed. If there's a net force to the right, then the speed will increase. If there's a net force to the left, then the speed will increase, but now to the left. And if the forces are equal, the force will remain constant. If there's no net sum of forces on the cart, then the speed will not change. This can also be seen in this simulation. I have a box on a skateboard and the guy is going to push on it. And we see that the speed of the box increases. When I stop pushing, there is no net force working on the box. So therefore, it will simply keep on moving. Now this is a bit strange. This is not what we're used to. In our reality, when we push something and we stop pushing, it also stops moving. The reason that it doesn't happen here is that there is one force that we have not taken into account here, and that is the force of friction. In this simulation there is friction working. When he's pushing, you see the orange arrow as the force of the guy, and the red arrow is the force of friction, which is simply pushing back. Therefore, the box isn't moving. To make it move, I need to push harder than friction can push. Now that is the case. The orange guy is pushing harder than the force of friction, so the speed of the box is increasing. When I stop pushing, the force of friction keeps on working on the crate. So we can see that the speed is now gradually decreasing. Let's do that again. I'm going to push on it again, increasing its speed. And now I'm going to decrease how hard I'm pushing until the sum of the forces is almost zero. And now we see I do have to push, but I only have to push just as hard as the force of friction. Then my speed will remain constant. When I stop pushing, then the sum of the forces is to the left, even though the crate is still moving to the right, and it will only stop when the speed is zero. So, our conclusions. Forces change the speed of an object. If there is no force working on an object, then the speed remains the same. And it doesn't matter if there's no force because nobody's pushing, or if there's no force because the forces that are working are cancelling each other out. As long as there's no force, the speed of an object will remain what it is, the same. That concludes our first explanatory video. I hope to see you all in class. Thank you.